Okay. So yeah, we're going to start off with inductors, which will be the final passive component that we touch on before we start getting into active components and then smaller actual circuit level items. So inductor, typical symbol, just a 4-hump system. Now an inductor is a energy storing device, much like the capacitor is, except instead of storing charges in like the capacitor does through its capacitive charge buildup, the inductor stores energy in the form of magnetic fields. Or as, yeah, in the form of magnetics. It has an inverse kind of relationship to voltage and current as the capacitor did. So like how we saw for a capacitor, we saw it resisted instantaneous changes in voltage. So our voltage curve rose while the current spiked and decreased over time, eventually becoming an open circuit. The opposite is actually seen with an inductor. So an inductor resists instantaneous changes in currents opposed to voltage. So that's will look, they'll have a similar curve style as before. The current rises exponentially while the voltage starts to spike and decreases over time. So this can be seen as it starts as an open circuit, or as an open circuit, and gradually goes to short. Which will cause voltage drops across the inductor to be massive at the beginning and allow no current to pass through, and then over time it'll eventually drop to allow current flow properly. So initially, when you switch it on, you'll see a large voltage drop across, basically an infinite voltage drop, so you won't see any current flowing on the opposite side of the inductor. But over time, once the charge is stored inside the inductor, current flows unimpeded across the inductor. So there will be essentially no voltage drop from beginning to end of the inductor. So in a DC circuit, it starts by completely blocking, but after whatever delay time based on in the inductance value. It'll be seen as extra wire. It has almost no impact to the to a DC system, aside from adding minor resistance in the circuit. However, when it's put into an AC circuit, because it resists instantaneous changes in current, we will see that the current in the system will lag behind the voltage. So we'll see a phase difference between our voltage and our current of the system, which is the opposite effect to what happens in a capacitive system, where in a capacitive system, you'll see that the voltage lags. So using something that we're not really going to touch on, power factors and kind of grid level energy storage and usage. But essentially, to be able to pull out or to send power into the grid, it has to be at the proper power factor. That's all about impedances, your inductance, your capacitance, your resistance. So if the system you have created to try to put power back into the grid, if it is too inductive, if your current is too far out of phase with the voltage, you would add some capacitance to bring the current back to a reasonable phase margin so it can be properly accepted. We're not really going to touch on that because I didn't really prepare anything, and it's beyond what we touch in the car. So, but just a little fact for what these curves actually mean when you're talking about current leading and lagging your voltage, and how the inductors and capacitors have inverse effects on those curves. So you can play with those two values to bring them to zero out.
I have a question.
Sure.
So you said in this case the current is lagging the voltage, is that right?
Yes.
Okay. I'm just confused because in the graph, to me, it looks like the current is in front of the voltage.
Now, are you trying to trick question me, or did I actually draw this wrong?
No, it's right. It's just confusing.
Yes.
Yeah.
So we say our starting point is the zero phase. So we can see that the voltage starts off first, and then you can see the current is coming in after. So the start point of the two is the current happens after. So if we were to start, if this is your time scale, at time 1, assume we don't have this and we just start it off. At time 1, we'll see some voltage, no current, and it won't be until time 3 before, same thing, time 3, before you start to see current shows up. So that's what it means when we say the voltage is leading or the current is lagging. Same thing there. So
I have a question.
Yeah.
So when you're designing a PCB, do you like care about the phase difference when you're putting in capacitors and inductors? Like, why should we care?
On our PCB level, we don't overly care, because with the values that we're dealing with, well, for one, we're not like, this is for AC signals. For DC signals, all it is turn on. You'll see the spike. You'll see the current slowly build up, and then it goes to its normal operation. So in that case, we don't really care for DC signals, which is basically all we're dealing with. And then even at that, until you start talking about higher power, like once you start to get up to grid level power transferring, that's when you start to care about having your systems in phase. But yeah, at our level, we don't care about this really at all.
There's a good application for this at the system level in the car, Mahmoud. Not really for board, but for example, from the battery to the motor controller, you usually have some long wires, and those wires themselves add inductance to the system. And too much inductance, when you're drawing current really fast from the battery, that current won't be just pure DC. It'll have a little bit of AC component, especially with a sharp rise. And so the inductance in those battery wires can add some like unwanted voltage spikes to the motor controller. And so what the motor controller designers do is within the motor controller, they put a lot of capacitors. And those capacitors act to cancel out the inductance from the wires in your system, and make sure that the voltage is stable and protects it from those voltage spikes that the inductance in the wires created.
But then when you put a lot of capacitors, could that cause the voltage to lead the current like in a way that you don't want it to?
Usually not in that application. More capacitance is helpful for those because you just have so much inductance that you're usually not to the other side where you have too much capacitance.
Okay, cool.
And yeah, and your motor is also a huge inductive load because it's just coils of wire as well.
Yeah, so for Mahmoud and any of the other members that have made an electric longboard or anything, on the VESC, you'll see those 3 big capacitors. That's doing exactly what Gabe just mentioned, because like Gabe said, wire is the simplest, is basically an inductor. So with that, anytime you're going wire to wire between boards, between battery to board to whatever, just the wire itself is an inductor. So inductance in a system is much more common. So you would just throw capacitors to balance that out. But yeah, that's what you see, those 3 big capacitors on your VESC. That's what that's doing.
Question.
Yeah.
I also have here. Isn't there also capacitance? Like when we were talking about resistors last week, you mentioned like a real resistor has an inductance and the capacitance, or in reality there is inductance and capacitance within that. Why do we just neglect the capacitance?
Yeah, so Again, all real items. They're not purely just whatever you say they are. They're not just an inductor. They only have inductance. It's not a resistor only. But when you're talking about, so when we were talking about capacitor, where did that go? Yeah, when we were talking about a true capacitor, it has all of its internal added everything. These are on the ranges of milliohms to microohms, like they're, or yeah, milliohms is a normal. The values are typically so small that they can be neglected, because like the added inductance of a capacitor is the same as just adding a little bit of extra wire in your system. So it's hard to truly keep track of, and it doesn't add a whole lot. So when you're wanting to actually figure out, when you're going about finding your general inductance and your general capacitance of your system, it's easier just to look at face value what your components are, because the internal added resistance, inductance, capacitance values are hard to keep in line, and also generally minimal, that it doesn't matter too much in the grand scheme of it. Anything else? Any other questions on this? Everybody good so far? Okay. And so your typical application, you'll see it for filtering, transformers, then relays, magnetics, and then, yeah, like we said, because all an inductor truly is just a wire, coil it and you'll get a magnetic field. The more you coil, the greater the magnetic field, the higher current you push through, the greater magnetic field. But there's plenty of there's more use cases of an inductor, because it is essentially all it is wire. It has more use case to it. Filtering, I'm not going to go over too much, because I think that's what we have planned for next week. Is I'm going to go over all the different filters. But just in general, filtering can be used in the sense like we just mentioned, to reduce any capacitance in a system, to balance out a system. If there's too much, you add inductance, or vice versa. It can also be used, like how the capacitor will be used. We'll see it for low pass filters, high pass filters, and a full range of other filters. But again, I'll touch these next week because I think that's what that plan is. Now, the other kind of filter that ties in with reducing capacitance is choke mode, common mode choke. Or even twisted pair cables are also kind of tied in with what a common mode choke does. Because you have some, whatever your data transmission line is, it's going to be a wire. So that in on itself is an inductor, adding inductance to your system, doing all of that. What you can do is have, if you're running your two communication lines, so like we said before, your CAN high and your CAN low. Since CAN is just a two-line communication, if you have to go board to board, you would twist your wires together, going when you send it off. This way, your wires will pick up noise together, and you can do some filtering based off of like differential pair, differential calculations and filtering. So you can see if there's a spike in one, you can catch that anomaly in both and exclude it from your signal. But that's where one, that's a slightly different use case. That's filtering on communication line. Since all of your pairing is just going to be wire sent out.
Hey, Jarod.
Yes.
Sorry, can you just repeat what exactly does the twisted two CAN lines do?
Sure. So, this is generally also referred to as differential pairing, or twisted wire, all the same. Basically, if you're sending your signals on your two lines, they'll have whatever data, they'll have whatever noise, a proper whatever. And if we have the wires not twisted, if they're just two separate wires running across the length, one may pick up interference and send on, and the other may not pick up that. This can distort your signal, and it'll give crap readings. You won't actually have adequate readings in this. If the embedded lessons touch on CAN or any of this in those lessons, you'll be able to see why this is terrible. This is bad for signal loss and what you do to combat. But if you do, so this is having the lines just run parallel or just loosely set up. If you actually have your wires twisted when you're going, you'll have your signal and it'll be able to pick up interference on both sides. So if you run this through your differential, filter, op amp, whatever the method actually is, it will basically flatten out. It'll detect the two peaks and cancel them out, because you're sending one as a positive signal and the other as a negative half. When you take the differential, you're basically able to cancel out your peaks, any obstructions, any poor signals, noise spikes, interference. Gabe can talk better on this.
Are those two peaks the noise, or is it the signal?
That'd be the signal, sorry. Yeah, so if a noise is induced, it'll peak to the same. And then that, when you take the differential of that, you'll be able to flatten out across.
Nice.
So basically, when you have the twisted lines, it allows for both of the lines to have like similar peak signals.
Yeah.
So that they can cancel out? Okay.
Yeah, it's for keeping your signal lines tight together, so any kind of influence, any noise pulses will be detected by both.
Got it, thanks.
Any other questions on this wiring / filtering? Okay, one of its other common use is a transformer. There's multiple uses for a transformer. One being to change your voltage levels. The other can also just be for isolation in a system, because a transformer is some windings. Why is it's some set of coils winding. The actual, what you would commonly see is some iron block donut where the coils will come wrap around on one side, and then you'll see the same on the output. So you'll have a V in, a V out. Depending on how many coils, how many turns you have on one side versus the other. So if you have, a 20 turn and then only a 4 turn, you'll have a voltage drop. So and if you were to change it the other way, you can do 4 to 20. You can create voltage increase or decrease based off transformer. But one of the more low-end practical kind of uses that we'll see is using it for isolation. So your V in, your V out will, in this case, will be same voltage, but you're able to have full isolation between the two halves. So this is especially good for any high voltage systems. If you wanted to control a relay or some portion of your system that has high voltage, you can go through a transformer, so you have your low voltage interacting with a portion of your system that's high voltage, while still just sending it a 5-volt signal across. Questions on how either the isolation half or the voltage conversion changes?
Sorry, I missed, what was that like line in the middle between the low and high transformer hand things?
That's just typical typical symbol for it. You'll also commonly see dots on either side, just for polarity.
Sorry, it's a standard symbol for what?
For a transformer or
okay.
isolation.
Okay.
But do we all understand how we're able to transfer 5 volts across this while still being isolated?
No, I don't get it.
Me neither. I don't
really get it.
Okay, good.
Sorry.
No, that's good. That's proper. I didn't explain it really. I just said it did it. So like we said at the beginning, since an inductor stores voltage as a magnetic field, we're basically able to, on one side, we're creating a coil of wire, and our output is just another secondary output coil of wire. We don't have anything inducing any kind of direct current on our output, but we are going to be feeding whatever power 5 volt AC at some current. And this is, in sense, what wireless charging is. You're inducing current into a coil, into coil 1, which creates a magnetic field about this coil. And it works in both ways, where current in creates magnetic. It works inversely, where a magnetic field in will create some current. So if we have coil 1 being fed some current, it'll create a magnetic field about it. And then coil 2 is able to pick up off of that magnetic field and start to induce a current on it in its own sense. So we now have a source of power coming through into coil 2 in the form of a magnetic field, and then we'll be able to see current flow coming out. A little clearer?
Wait, so what was the thing about like high and low? And like how does that work?
So high and low was just the example in this case, because its typical use case is for isolation, because these two systems, like these two coils, are technically not electrically connected. They don't share the same power rails. They don't have to share the same ground. They can be fully isolated from each other, so that the one half of your system can be driving in the low voltage portion of your circuit, while the second coil is able to run high voltage electronics that may be on the other side of your board, because you don't want to mix high voltage and low voltage in one plane. You don't want high voltage ground and low voltage ground to be connected, for various reasons. There's safety concerns. There's also general added noise that can be induced, and easier potential failures in components when you're mixing high and low voltage. So this is just for saying that we can isolate these fully to drive a low voltage and a high voltage system. But these technically have no meaning, just as the example.
Okay. Thank you.
But to the rest, that this clears it up a little bit more.
Yeah.
Yes.
So the actual transformer will look something like this, where it's laminated steel sheets creating basically a donut that coils off of one coil off the other, so that the induced magnetics goes through the metal, because the laminated steel sheets are better conductors for transferring the fields, whereas if you were to do, like for wireless charging, how it's just through air, air is a much weaker kind of medium for the magnetic field to flow. So the power across an air gap will be much lower than it will be when it's around a solid steel core. So when you actually see a transformer, it'll be typically in some laminated steel core donut. And then on to the last thing on inductors. I'll go on relays. Yeah, a relay, again, it's a mechanical switch. So you're able to control a switch based off of a low voltage system. So this is major for controlling high voltage systems with a low voltage signal. So this is what our errors are, our accumulator isolation relays that we use in our car. Because we're able to switch our 168 volts across a switch with only using a 12 and have them fully isolated. So they're not going to impact each other. We're not going to have an accidental short high voltage to low voltage. But we're able to control the switching of 168 volts and beyond with only 12 volts. And the activation of that is, again, just a magnetic coil with basically a metal plate that it's, yeah, how does it go? So when we feed some current into our coil, we're inducing a magnetic field. And if we have a metal tab, it's going to be attracted to the system. So we'll have the metal make contact. So the switch is closed. So when we send a power into our low voltage side, the relay will close. And typically these are on springs. So as soon as we cut off the voltage, it'll be forced back up, be open. But this is a very practical and quite frequently used application of being able to use low voltage power through just a magnetic coil to be able to switch much higher voltages than would otherwise be capable.
Jarod, what's
Yes.
airs? I'm assuming it's not shoes.
It's so that's airs is simulator isolation relay. All it is, what am I doing? Really? It's just what we call it in the rule book for a car. Like that's what we call it for the car. All it is a relay. But saying it's an isolated relay from our battery pack. So in our actual system, we'll see it as our battery pack, our plus and minus, and then we have our two airs before it goes to inverter and all the extra, motor and everything.
Okay.
But yeah, it's just the relay that is how we call these relays for this
Got
day.
it. Thanks.
Okay, that's everything I have for inductors. Any final questions on it? Do we all understand how a magnetic field is actually induced through this current path? How it's able to actually attract such arms in a relay? How it behaves with instantaneous switching? Are we all good with all of this? Okay. Then I'll move on to Snubbers. If I can find my okay. So back half of this. Snubbers. There's a chance some of you have seen Snubbers before, but never realized this is how they were actually called. But there's 2, 3, yeah, we'll say 3 main kind of snubber categories. There's diode snubbers, there's RC, so just resistor capacitor, and then RCD, so resistor capacitor and diode. And all a snubber does is it's typically placed in line with inductive loads, typically motors, relays, or any other high inductive systems. So starting with the diode snubber. And then this will, in a simple case.
Wait, are these flybacks?
Basically, yes.
Is that what a snubber is?
Yes.
Oh.
Yeah, so that's the other thing.
I've literally never heard the word snubber before.
Yeah, so for if it's simply a diode, these are typically known as flyback diodes. They're nothing special. They're not a different type of diode. It's still just a diode. But if it's only a diode being used as a snubber, that's typically how it's known. But when we're talking snubbers as a whole, it's all the different variations that we can possibly get. So how the basic function of it, if this is, say, a simple electromagnet or any high inductive load, current will typically just flow through the system, assuming our MOSFET is, we're sending it on, so the MOSFET is actually, or it's a better case, ignore the actual function of a MOSFET. All we're doing is using a switch. So when our switch is closed, current is able to flow through the system, functions like normal. Because we have our diode facing against our power source, there's going to be current's not going to want to flow through the diode because your voltage on the side of it is greater than on this side, so it's going to block any current flow. So all the current is just going to want to go through our inductive load. Now, when we get to the point of opening our switch, there's still going to be some built-up charges within our coil, because again, it doesn't like instantaneous changes to current. So we will see some current flow, some power left in our system. So if we have, now that we have switch open, we don't have anywhere for that current to go. So by adding this diode, we now provide a current path for the coil to be de-energized. Just a path for the stored energy to be dissipated in. Doing this allows the energy in your system to be dissipated so the coil actually turns off faster. Because if we were to assume this is an electromagnet or even a relay, and we don't have a diode, or we don't have any snubber, there's still going to be current. It'll take much longer for the current to dissipate just naturally. So there will be built up charges, so there won't have an instantaneous reaction to us opening the switch. It'll still carry on. It'll still carry its current for a little bit longer than it should, which can cause problems if we're wanting instantaneous switch off. So if we have a diode in path, because the diode has some internal resistance, it causes a voltage drop. It has some internal, because it has that internal resistance, it's able to eat away the current. Other typical applications will have, sometimes you'll see a resistor in line with the diode, so that it can dissipate faster, or have a greater current draw. But everybody understand that much? Getting the current path?
Wait, so what did you actually define what a snubber is? What?
So, so a snubber in its actual sense is, I wouldn't say a device. It's a circuit, or a portion of a circuit, really, used to de-energize inductive load. So that's why it's typically seen with electromagnetics, motors, relays. It's just a system that's used to de-energize your inductive loads, creating a current path for the current to still flow after opening a switch. But yeah, all it basically does is to create a current path for that stored energy to be dissipated.
Wait, Jared, so the snubber is the part in the diagram, like, not including the switch part? The switch is kind of just like an application for it?
So that part is the snubber.
Oh, okay.
Yeah, you'll typically, like, if you weren't to have it any other way, you would just have your electromagnet or whatever it may be, a switch going to ground. That would be your typical, that's what you're actually using. Just an electromagnet connected to power, going to a switch to ground. And then by adding in this extra circuitry in parallel with your inductive load, that's what the snubber is.
Okay. So wait, when we have the, like, if you go to the, like, first diagram that you drew, so when we have the switch, basically it, like, opens and closes due to this whole, like, setup.
This switch?
Yeah. So it just like keeps opening and closing, or
No, so this switch is manually controlled.
okay. Okay. So when it's open, then it goes through the other part of the circuit and de-energizes, or just the energy is dissipated.
Yeah.
Okay, gotcha. It's the other way around. Flipped it around.
Yeah, so this, that's why I first drew a MOSFET, because like we'll see, a MOSFET is just an electronic switch that we control by setting its power or no power. But yeah, so this is, we are flicking a switch, whether we want this on or off. If it's in the sense of, if this is an electromagnet, then we obviously want to, turn it on so it can pick up some metal, maybe move it somewhere, turn it off so it drops it. So we are manually switching it on and off. When it's turned on, it flows like normal, allowing a current path, allowing it to function. Turn it off, and we just give it a place to be discharged.
Jarod,
Yes.
did you sneak in a resistor behind the flyback diode?
Yeah.
Okay. So is that always going to be the case?
No, sometimes, a lot of times it'll just be the diode.
Okay.
Because it has its own internal resistance and it causes a voltage drop on its own. In a lot of low voltage, or when the switching time isn't too fast or too critical, you'll typically just see a diode. But once you start to want to start switching faster, maybe, you may add a resistor to dissipate the power faster.
Okay, makes sense. Thank you.
Will it generate heat when doing that?
What?
When you de-energize the inductive load, will it like release like a lot of heat or not many? I mean, just heat.
It won't dissipate too much heat. I mean, depending on the voltage in your system and what resistance values or any of that you're using. But typically, when these, like the magnet, or I keep saying magnet because that's its most used, your inductive load will generally run its hottest. Because if you only have, 100 ohm resistance in this case, it'll only draw as much current as it wants to, or as it allows. So you typically don't have to worry with heat. Also, the discharge current timing is generally sub 1 second. It's generally milliseconds that you're discharging. So it's not a long switching process. It's not a high power that's over some amount of time. These systems are generally milliseconds to discharge. So power levels aren't too crazy. The other Snubbers, if we look at it the same way, is the RC snubber. I actually haven't seen these all too often, or much at all, really. But these, I believe these are typically polarized caps, such that blocked. No, that wouldn't be proper. You'll have some small capacitance, such that when you instantly turn it on, some current will flow into charge your capacitor, and then once your capacitor is full, it'll block any voltage flow like we saw. So since we're going to block any current flow once it's full, we'll go across the inductive load when your switch is closed. But then again, once we open our system, we have a path for the current to flow. It works basically the same as what the diode did, except in this case, the capacitor causes minor bypass initially. So power isn't immediately sent through the inductive load. I'm not 100% familiar with an RC snubber, because again, in most applications, I've seen it as just a diode or resistor diode. But this is one other application using an RC.
Do you know why we'd ever choose this one as opposed to a diode?
I believe it's for, I'm not 100%. Gabe, have you ever seen RC snubbers?
Nah, this is bullshit.
So it's just usually just diodes then.
Spitting fire, Gabe.
Yeah. I don't know. Apparently it's a thing. I've mostly just used diodes, but from a quick Google, there's something about like maybe absorbing some high frequency transients from through the capacitor.
I guess noise as well.
Yeah, maybe
There's
noise,
something with noise.
something like that. I don't
Something
know.
sounds right. You're using a
Electronic
capacitor.
somewhere. And yeah, that's it. No, that's all I know.
Yeah, like for the final one, the RCD, this is one that I've actually used at work in one of my designs, where again you have your diode in parallel, and then you also have your resistor capacitor in parallel. So it functions the same as the others. When you want it, current flow, otherwise through the system. And yeah, so the use case of this is for when you're switching at higher frequencies. So I suppose it is more on the cap that you're caring about higher frequency suppression. So yeah, so for faster settling times and for lower ripple voltages. When I actually did, I don't have it set up, and it take me a minute. I did a quick comparison of an RCD versus just a standard flyback diode snubber. Just using some bullshit values at a 5-volt circuit. The RCD is able to de-energize the system in 5 milliseconds, while just the flyback diode took 20 milliseconds to de-energize. So we are able to see between just having the diode and including this extra capacitor resistor in parallel, in series with the diode, we are able to reduce, de-energize the system faster. But again, it's on the order of milliseconds, so only in so this is more typically used in transformer switching instead of electromagnets or motors, because you can have transformers, again, for their isolation. You would use those in power supply, step-down converters, typically, isolated DC-DCs. So if you're switching that on and off, as we'll see, that's how buck converters work. If you're switching that on and off at a high frequency to achieve the step-down voltage, including the RCD system will allow your system to de-energize faster, so that your output voltage actually goes to the expected. Because if you try to, if there's still some voltage left stored up in your inductor when you turn it back on, the time to reach full power again in your inductor will be less than if it was fully discharged. So that can throw off timing circuits, or time critical circuits.
Wait, this is just straight up a buck converter. Is it? Is it straight up a buck converter and how it's connected?
This setup, no. There's more to do to make it a buck. Or different orientation, really, to make it a buck.
Yeah, different orientation. I'm just pretending that it is. The second you mentioned it.
I mean, it's close.
It is close. It's like parallel resistor. Oh shit! Wait, what? So it's like strictly a better version, or not better, like a faster version of just a flyback diode.
Yeah. So what you typically see, just the flyback and the RCD is purely speed. They'll achieve the same thing discharging. This one is just faster discharging.
Why is it faster discharging? It's because the cap also de-energizes.
Yeah, something about the
Cap then pushes the current into the thing and does make it faster. I don't know. Just pretending. I'm just thinking about electrons at this point.
Yeah. Again, in most cases that you'll actually consider or use this in, this is enough. You almost never actually need to do a full RCD speed. It has the added benefit of faster discharging, but I don't know enough about them to say why or how they actually achieve that faster discharging.
Jarod,
Yes.
what does faster discharging mean for us? Like, how is it beneficial?
So if you want, basically, if you want to be able to turn this off and then back on again in a faster period of time, since you want it to be fully discharged before you turn it on again, you want it to faster discharge in that case. So, I mean, I can quickly draw up, so I'll quickly explain up a buck converter. We'll go into this in detail, so I'm not going to spend much of any time on this. Inductor out. So this is a buck converter. You have some voltage on your in, and you're going to have some voltage on your output that is going to be lower than your input. In BASIC, that's all you're doing. It's dependent on what your values for your components are. And then it's also dependent on how fast you're switching this on and off. So if we were to take this a level further and say we wanted to make this isolated from whatever is on the output, there's other transformer styles of the buck converter. But if we basically wanted to have our output be isolated to something else in our system, we want our coils to de-energize completely before we're switching on and off. So we want, and since this happens at multiple kilohertz and above, it's a fast switching frequency to be able to regulate your output voltage. In that case, you may need your coils on the output to discharge fast enough. In the car, we don't have to deal with anything that fast. Since we're not doing any transformer isolation, we're not doing any fast switching electromagnets. So again, in our case, just the diode is good enough. We're not at any extreme levels where we care about this fast discharge.
Jared, this might be a dumb question, but does it matter what side the humps of the inverter go on?
What side the which, sorry?
Wait, what?
You mean inductor?
Of the inductor, there's the bubble parts.
Oh,
Does it
how
matter
I'm
what
drawing.
like face?
No, the standard is going if you're drawing it flat, it's facing out. But yeah, like it doesn't matter.
It's just a drawing.
Okay.
Yeah, it's just a 4 bump, whatever, going down. So it doesn't matter.
But like when you connected in like an actual circuit, it doesn't matter like which way you connected, right? Like with diodes or LEDs.
Yeah, no, these aren't, or some are polar. Your standard inductor is non-polarized, because again, all it really is wire, and then it goes into the housing, and all it is a bunch of wires coiled up to the output. So a coil of wire isn't really polar. So there, in most applications, in most standard inductors, there is no polarity. Sometimes for like common mode chokes or components like that, there is a polarity, but even then, I don't think I've really noticed. Questions from someone else? Anybody else that hasn't said anything this entire time? Is it all making sense?
Can I ask one more thing? It might be dumb.
Go for it.
Can you just scroll up just like a tiny bit? Yeah, right here. What does faster settling and low ripple voltages mean?
Like we saw at the beginning with an inductor, as soon as you turn it on, you see a high voltage spike and then it dies down. So and then the opposite is seen when you turn it, when it's on to off, you'll see a high negative spike. So when you're switching it on and on, if you're switching it on quickly, you'll see a lot of spike and then it'll go and then spike. It may not be that drastic, but by adding, since you add the capacitor into your system, which acts oppositely, it doesn't like changes in the change in voltage. It basically reduces these spikes, so you get safer levels or more tolerable levels of voltage spikes. So that's what it means by lower voltage ripple, because you can see this has a large ripple, whereas this now has a smaller ripple. So that's what we mean by ripple voltage, and that's how the capacitor helps that. And settling time is just how long it takes to discharge. So in the actual, if we are to look at the, let's one more time. If we're looking at the voltage across the inductor, as soon as we close it, what we'll see is some voltage rise, and then it'll stay constant. And then as soon as we open, depending on if we have just the diode, it may be a drop that takes, that long to discharge. And then if we were to have the RC network in there as well, that would be able to increase the switch off time. We'd most likely see something where it's now de-energized by this point. So the settle time, the time that it takes to get to the 0 volts or the neutral, it's now settling at this point. So we can see the time is less in the RCD because it reaches its settled 0 volts faster.
Got it. Thank you.
Oh, you did understand what you did know why. This makes sense.
I don't know
Um,
how though.
oh, yeah, this kind of makes. Well, does the difference between the green line and the blue line like a different capacitor value? I'm assuming.
No, green is just diode.
Oh, just diode.
Yeah, we're
Wh-
saying
How would you
green.
choose a capacitor value then for the circuit for this subber?
There are equations for it. There's online calculators.
Ah, okay, perfect. I don't have to do the calculation.
Yeah. When you're doing this, I'm pretty sure your capacitance is meant to be low um, in the microfarads, with the resistance low as well, like sub 100 ohm. So, yeah, I'm pretty sure when you're doing the RCDs, it's like less than 100 ohm and some microfarad capacitance.
Mm,
But again, there's equations and there's online calculators, so
perfect.
it doesn't.
Less work. Oh, question.
Yes.
What did you? I'm not sure if you can disclose this actually. What did you do What did you do in your project at work that needed you to do this kind of circuit?
So I was doing kind of as described. I was doing an isolated transformer buck converter.
Oh, okay.
Um, so yeah, like all it was is just a buck converter, but going through a transformer. So we're just
Was it a buck converter on one side and this subber on the other?
no. So it's there was a circuit that kind of has some switching integration into this,
Mm-hmm.
and you're kind of able to merge. Like it's not just buck converter output and then you go output to transformer.
Mm-hmm.
You can kind of switch the transformer, so you can kind of throw the transformer into this system,
Oh.
basically, kind of taking over. Because the output voltage on your inductor is your actual output voltage.
Mm-hmm.
So if your inductor is now one side of a transformer, you're able to have basically your other side. There's more to it. And I mean, if we want, I could prepare, like when we get into that session, I could prepare how a transformer buck converter looks.
Ooh. That'd be cool.
Yeah, so I can add in that into that lesson, just a quick how that looks. But it's basically integrating a transformer into your buck converter design for isolation and that kind of stuff. So, but yeah, that's all it really is. But since your switch buck converters are going at multi kilohertz plus, it's timing.
I see. That makes sense. Thank you. Okay, how sorry. Another thing actually. When you say high speed switching, like the subber with the resistor and the cap is designed like you're dissipating power a lot faster.
Yeah.
When you're using when you're powering when you're switching it really when you're switching the inductor on and off really fast like a PWM motion, wouldn't you want the faster discharge? Why is it? Yeah.
Yeah, if you are switching at a high frequency, you want faster discharge.
Okay. So when you're designing like a motor controller circuit, you'd want like the faster discharge, the subber.
Yeah, in cases where your inductive load is being switched quickly.
Okay.
You would go you'd want a faster discharge.
So you'd see this in PWM circuits then, this type of subber.
Even at that, because like I said, like doing a quick like bullshit kind of
Like test that you did.
yeah, simulation, even like it was 20 millisecond settle time versus like 4 millisecond settle time. So like your it's not super critical, and it's but yeah, once you start getting to that higher frequency, it really starts to show.
Yeah, it sounds really like critical in higher frequencies because you're repeating this like a shit ton of times in a second, so that'll add up. Like you'll see the difference between like actual like one will slow down faster than the other, or it will be more responsive than the other at least.
Yeah.
Okay, cool.
Okay. Anything from the rest of you? Faraz, Braden, Raphael, Koi, any comments? Questions?
Clear as mud.
Yeah, it's pretty clear.
As mud.
Have you never heard
Yeah, that makes sense to me.
Never, Brent. Have you seen Snubbers before, or have you at least seen the diode, the flyback diode?
I've seen them. I've never actually heard that name before. I'd never heard the name Snubber before. I didn't realize that's what they were referred to.
Yeah, most people don't, or most people haven't, because it is much more commonly just known as a flyback diode, since that's the simplest version of it and the most used.
Yeah, but yeah. I knew their functionality. I just didn't know their name.
Yeah, that's general.
Is Snubbers like a nickname, or is it like an official thing?
No,
'Cause it sounds like Snuggles, like Snuggles, Snubbers. I don't know. That's what I
I mean, to be
associated.
fair, like this is the first time I've ever heard the word snubber. I
So
just know
funny.
the flyback diode, so he could possibly be making this up.
Snubbers is the proper term for what's forgotten on here.
Really, he just wants to see how many of us he can make look like idiots in our next class.
No. In our
Probably.
co-ops, you
In
walk
our
up to your
co-ops.
like
Have you
engineer and
heard
be
of
like,
Snubbers?
it's like, oh, should I put a snubber in that? A fucking what?
To test how much you guys are paying attention and due to you.
Hey, we pay attention. You're happy.
Okay, so cool. We're all done.
Yeah. So this is the end of today's lesson.
Cool
Can we
beans.
see your dog now?
Oh my gosh, do you have your dog with you? Gosh.
Dog?
I do not.
No.
Yeah,
I feel like you're lying.
I feel like it's literally in your lap right now. And you're like, nah.
That's a lap dog.
No, it's a puppy, so it's annoying. So
It's even better.
Exactly.